So a little bit more on conservative and non-conservative forces and how they relate to energy, and then some focus on the relationship between force and potential energy. So non-conservative forces cannot be expressed as a potential energy function, but they result typically in a change in the internal energy of the object, most easily revealed in the example where you have friction and you're adding energy, heat energy, to an object because of the frictional resistance. So internal energy, change in internal energy, is usually a change in internal energy unless the forces are conservative. It's equal to minus work other. So we put work other into the overall energy balance equation, and now we're relating change in internal energy as being the negative of that. Keep in mind that work done by friction is negative. So this work other, if it's friction, it's negative. And then the change in internal energy would be positive because as a result of friction, sliding an object on another, that object will gain heat energy. So that internal energy change is a positive change. Hope that makes sense. So we have K1 plus U1, position 1. Instead of plus work other, we'll say minus delta U internal equals K2 plus U2. Total energy change, right? We can express as the changes in the mechanical energy, delta K plus delta UG. So here we have the piano falling through the air, well, don't worry about air, falling through a gravitational field, a conservative force field, with a force mg. And if there was friction force, like air on it, then that's force other, and that's associated with work other. If it's just conservative forces, the delta K and the delta UG, or delta U period, that's zero. From the conservative forces, there's no change in the mechanical energy. But this does change mechanical energy, this work other. So this force is actually, what it's really doing is reducing the kinetic energy that would otherwise be there. The potential energy is being lost as it falls down, but it's not all transitioning into additional kinetic. Some of it is being lost from work other. But that force is not a conservative force. So we still can think of these two conservative forces, namely, well, the one conservative force, gravitation, as, in this case, decreasing the potential, increasing the kinetic. Simultaneously, this is taking away some of the kinetic. So that's delta K plus delta U minus delta U internal. We just flipped the sign from the work others, all we did there. Then change in total energy is equal to minus delta U internal. That's what we're left with. Delta K, delta U are both zero. So we have delta K plus, so the change in kinetic plus change in the potential energy from whatever conservative force we're talking about, plus the change in internal energy altogether equals zero. So that's perhaps the most far-reaching, or, well, that's not true. As far as what our discussion is going to be limited to, that's the most inclusive equation that we'll encounter for energy. We're not going to worry about relativity and other effects like that. So this is only if conservative forces act, and then delta U internal is a result, a change in energy result from non-conservative forces, and that's equal to minus work other. We now consider the relationship between force and potential energy. If you remember week 1 of AP Physics, we actually learned the math of this. I said it was going to be very important, and so we're in the middle of it now, actually toward the end of it, and you're going to see just how easy it is to find this relationship. So we start with the idea that we've already discussed in some detail, that the work done by a conservative force is negative change in potential energy. As an object falls through the air, through the sky in the gravitational field, say an object falling toward the earth, the potential energy decreases, gets less, while the work done by the conservative force is positive, because it's moving down while the force is down. So all that should be well understood. So we have positive work done leads to a reduction in the potential energy. You can relate that to springs really easily also. Well, let's consider the dimensionality of work. We remember that work is a force times distance. So let's limit it to the x direction. And then it's the force times delta x, force times distance. That's approximately the negative change in U, simply because you should know that Fx could be changing over delta x. So we need to be a little more precise, and you know where that's going, don't you? That Fx is approximately equal to negative delta U over delta x, which again is now the form that you've already seen for this relationship. That's what I mean by being easy to get to. So in the limit, as delta x approaches 0, the Fx as a function of x is just the negative derivative with respect to x, the potential energy. So there it is. And that's a very powerful equation, and it was very easily derived. The significance is that a conservative force always acts to push the system toward lower potential energy. And now I want to demonstrate how we can see that taking place. So let's consider a marble moving along the x-axis, and we're going to consider the potential energy, which looks like that. And this is potential energy with respect to x. So where is the force on the marble? 0. And let's defend where a position of stable and unstable equilibrium is. So let's look at that. So we have some pertinent positions, A, B, C, and D. These are going to be our choices. We start with the idea that Fx equals minus du dx. Well, since we're looking for places where the force is 0, we need this to be 0, the derivative to be 0. Well, that's clearly at B and D, because at B, the derivative is 0, and at D, the derivative is 0. The slope is 0. And now a statement I'll make is that a minimum in a potential energy curve is a position of stable equilibrium. So I'm suggesting that at B, we have stable equilibrium. The force is 0. Well, one way to think about it, think of this spatially. If this is a situation where there's a gravitational field acting, and this is potential energy, but it could also be related to height, because there's greater potential energy at greater height and less at less height. So we could consider this in a gravitational field, and this would be the y-axis. In that case, this is like a bowl sitting on a table. And of course, if you have no force acting at B, at that point there's no force acting, that's going to be consistent with no change in potential energy. 0 change in potential energy with no force. You need forces acting while it moves through space in order to have that be non-zero. So this is 0. Now, at the bottom, let's consider at B, of course. We have minus du dx is 0. And now let's go to the left of B. So here's B. We go to the left of B and consider what du dx is. Well, du dx, the slope of the line there, is negative. So minus du dx is obviously positive. All right, well, if it's positive, that means the force is greater than 0. So the force is pointing in the positive direction, to the right. The force is moving to the right because negative du dx is positive, and that is the force. So if this is a bowl, and we put a marble in the bowl, you know the marble actually goes back and forth like this. And consistent with that, if we're over here to the left, with the force being positive, pushing it this way, it pushes the marble to the right. Down here, it's not being pushed at all. But if we're over to the right, then negative du dx is positive. Negative du dx is negative. And therefore, the force is negative. The force actually points to the left, pushing the marble to the left. And there you go. So that hopefully makes it clear how that works. So let's finish the problem by considering a position of unstable equilibrium. So again, keep in mind that this is stable here because as you deviate from the position of equilibrium, the forces acting on the object tend to restore it back to that equilibrium position. Simple as that. Now, if this is a position where you consider it a bowl upside down and it wants to roll off in both directions, let's see how the equation confirms that. So we have a maximum in a U-curve is a position of unstable equilibrium. So at D, negative du dx is 0. Let's go to the right. We go to the right. Du dx is negative. So negative du dx is positive. So the force, if it moves over here, the force is in the positive direction, shoving it away from that position of equilibrium. Force is greater than 0. It pushes it to the right. And of course, then, if the position is to the left, du dx is positive, making negative du dx negative. The force is less than 0. It gets pushed to the left. So just to confirm this relationship between force and potential energy functions, a couple of simple energy situations. Here we have potential energy mgy, the object going from position 1 to position 2. U is mg, basically delta y. Well, that's the change in U. Starting from a reference equal to 0, it's just mgy. So here is a graph of the potential energy with respect to y. So that's pretty simple. And how about the force? Well, the force is the negative derivative, the potential energy function with respect to y. And if you take the derivative of mgy with respect to y, you get mg, so it's minus mg, and here it is plotted. So there is the obvious connection. Let's do it for a spring. In the case of a spring, we have u is 1/2 kx squared, so it looks like this. And what about the force? The force is the negative derivative of the potential energy function. There it is, minus du dx. And so that is, bring the 2 down, multiply by k, and you have x left, minus kx. And you've already known that to be the force associated with a spring. So it looks like this. Let's consider a problem where we have 2 charges. One is fixed at the origin, and the other one is free to move. So charge number 2 is free to move along the x-axis. And let's find a force equation for what charge number 2 is experiencing if the potential energy function is c over x. So force is minus du dx. So that's minus derivative of c over x. And that's minus d dx of cx to the minus 1. We'll bring the minus 1 down. It'll cancel this negative, and that'll be x to the minus 2. So that is c over x squared, which is Coulomb's law. This is what Coulomb discovered. And the force is positive, which is also repulsive. That's assuming that the sign is the same here between these charges. Now answer the following question. Fundamentally, what is c in this expression? That's right. It's the magnitude of the forces. The magnitude of the charges in coulombs, it turns out. So how big the charges are. All right, if x goes up, of course, then we know that u goes down. So as it gets, basically this charge is getting pushed away. So the force shoves this away, making the distance larger, and the potential energy goes down. And we will encounter in E&M that since this is the force, then by definition this must be the potential energy function. So this isn't just a hypothetical, but this really is the potential energy between 2 charges associated with the electric field. So it's inverse distance. That's what the potential energy is proportional to. So that's kind of interesting. Not to be too redundant, but again, the spring, 1/2 kx squared, and if we take the derivative of that, we get minus kx. And this happens to be Hooke's law for the force of a spring acting on something else. And this is Coulomb's law, the electric field force acting between charges. And now a brief consideration of force and potential energy in 3 dimensions. We usually just have a single dimension, like Fx, which is minus change in u divided by change in x. Well, force is a vector quantity, so we could have that there's a force in the y direction as well, minus delta u delta y. Fz is minus delta u delta z. Now in the limit, as the delta spatial dimension approaches 0, you know that we have the derivatives. What we're going to do now is consider each of these dimensions independently, and we get a new idea known as the partial derivative. So fx is equal to minus partial u partial x, fy is minus partial u partial y, and fz is minus partial u partial z. So again, these are partial derivatives, and the idea is pretty simple. It's that this potential energy function is related to 3-dimensional space. But since you get the force, and force is a vector, you can consider the change in the potential energy function just in the x and relate it to force x, and do the same with y and z. Each time you're doing it, when you do it with x, you're ignoring what's going on in the y and z directions, that there's a change in the potential energy with respect to y, there's a change in potential energy with respect to z. You ignore that, you treat them separately. So they're partial derivatives. You're not taking the full change all at once. So it's not too difficult of an idea. And then we get an overall expression that specifies to us what all of these combined are, which can be written as follows. So the force is equal to minus all the partials. So we have partial in the x, I, partial u partial y, j, partial u partial z, k. Now this entire partial derivative operation for 3-dimensional space is known as the gradient of u. So the force is the gradient, the negative gradient of the potential energy function, or grad u, as it's called. That upside down delta is grad, or otherwise known as the del operator. Thus we can express the force as simply minus grad u, and that symbol does a whole lot for us. It incorporates the partials in all the dimensions. Now, if you're a little bit confused, this really translates very easily in practical situations that we deal with. For instance, if we want to know the force in the x associated with a spring, generally that's a single dimension, namely x, so we have 1/2 kx squared. Well, thus we have the force in the x equals, we can apply this gradient function to 1/2 kx squared. Let's go ahead and do that. Here it is all written out in detail. Partial of the potential energy, partial x in the I, partial yj, partial zk. But if you look at this, with respect to y, this is just a constant. With respect to k, or z, this is just a constant. So this whole thing simplifies down to minus kxi plus 0, and you have what you knew it was already, which is simply the force being minus kx. Let's apply this partial derivative idea to a simple problem. Object moving in the xy plane, acted on by a conservative force, and the potential energy function is as given, and we see 2 dimensions, x and y. So the force is going to be the minus partial in x and y. It's a function of x and y. So that's equal to minus grad u. In this case, grad can be written in terms of the I and j unit vectors. Adding the k unit vector partial would do us no good because there is nothing in that dimension. So it's a 2-dimensional problem. And the derivatives, the respective derivatives of x to the minus 1, y to the minus 1 is easy. It's going to change the sign and we'll have inverse squared. So this is alpha over x squared I plus alpha over y squared j. So that was pretty easy, wasn't it? So this will conclude our little segment on conservative forces and potential energy functions.